Well, if an AC circuit contains only resistors, then it's really no more complicated than a DC circuit. We can solve an AC circuit that is resistive only using Ohm's law and Kirchhoff's law. However, when we introduce other components, then the situation becomes a little more complicated. So let's consider another component. Consider the capacitor. A capacitor stores electrical energy in the form of charge, and as a result, the voltage across the capacitor is out of phase with the current. And we can see that in this diagram here. In a capacitive circuit, the current leads the voltage by 90 degrees. So there's a phase difference in the current as compared with the voltage across the capacitor. And this can be seen if we look at these waveforms on an oscilloscope. Now, if we want to analyze a RC circuit, meaning a circuit containing a resistor and a capacitor, turns out that the easiest way is to use a phasor diagram. As you know, in any series circuit, the current is common. So here's our diagram now. We have an AC source, a resistor, voltage across the resistor, and the capacitor with a voltage across the capacitor. Okay, and we're going to draw the current phasor as the reference because the current is common throughout the circuit. And because the voltage across the resistor is in phase with that, then the VR, the voltage across the resistor, will also lie on the positive x-axis. And we know that the voltage across the capacitor will lag the current by 90 degrees, and so therefore we're going to draw it on the negative y-axis. So here is a phasor diagram for the RC circuit. We have the current drawn on the x-axis for reference. The voltage across the resistor is in phase with the current. The voltage across the capacitor lags the current by 90 degrees. And then we have the source voltage. Now, how do we come up with this phasor for the source voltage? Well, we know from Kirchhoff's law that the voltage drops in this circuit. Of course, we have voltage drop across the resistor and a voltage drop across the capacitor. So the sum of these voltage drops must equal the source voltage. But we cannot simply add numerically because these voltages are out of phase. It turns out what we need to do is add the phasors. And as you know, phasor addition, as we learned in the previous video, is accomplished by transferring one of the phasors to the tip of the other phasor. So imagine transferring this VC over here, and then the VC points from here down to here, and then we see that E must be the phasor sum of those two voltages. Okay, and that's given here. So let's look at an example now. We have VR is 6.7 volts, and VC is a negative J 5.1 volts. Okay, and we need to find the source voltage and the phase angle? Well, we could do this geometrically if we had graph paper and we could draw very well, but it's a lot easier just to do it algebraically, because we know that the sum phasor, the magnitude of the sum phasor, can be found by Pythagorean theorem, and the angle can be found using the inverse tangent, which we looked at in the previous video. Okay, so there is the magnitude, square root sum of the squares, 8.4 volts, and the phase angle, inverse tangent of 5.1 divided by 6.7, 37.3 degrees. Now, it's a matter of convention that the phase angle in a capacitive circuit is treated as negative. But in this course, I'm not going to quibble about the sign. So as long as you come up with the correct magnitude for the phase angle, I'm not going to worry about the SIGN of the phase angle. Let's do one more example. Now we're given source voltage 17 volts and voltage across the resistor 15 volts, and we need to find the voltage across the capacitor and the phase angle. Okay, this time we need to do square root difference of the squares because we're given the hypotenuse. So it's 17 squared minus 15 squared, and that turns out to be 8 volts. And again, conventionally we have the negative sign here, but if you leave out the negative sign, I'm not going to be too concerned about that. And then the phase angle, capacitive voltage divided by the resistive voltage, and then take the inverse tangent. The answer is 28 degrees.